So, well, as some of you saw, I graded a whole bunch of quizzes last night to get up to date. Well, I've gotten some revisions since then, so I still need to do that. I started grading finally the Chapter 4 homework. I'm You're on YouTube. I'm still working my way through those. It was interesting to get multiple copies of the exact same code, um, especially when the code is incorrect. And it reminds me of one word that's often tossed about these days when discussing what goes on in the world, groupthink, which is basically a word used by contrarians to justify them thinking horrible things. But anyway, but it's almost like here we have group non-think. So, yes, I might want to, as you're working together these problems, which is fine, to like examine things a little more critically. So when I finish grading those, I'll be sending each of you emails like I normally do that has where you messed up. But yeah, it's just, I was literally, as I finished grading one student and move on to the next, I was literally copying and pasting comments from a previous student because it was the exact same mistakes. So in a lot of cases. So I guess it speeds up my process, which, so thank you for that. Yeah. So, okay. Are there any homework questions about anything? Because I know that chapter 5 is still going on.
For the MinRes, GMRes one, can you explain a little bit what the difference in those two is? Like, it's supposed to be really similar, but like one thing's different than.
Okay, let me look up a question.
It's 5.3.1 is the MinRes on top of
Wait, 5.3.1?
unless I wrote it down wrong.
Well, okay, because that's just a coding question.
Right.
Okay, hold on. Okay, so I signed 1, 2, and 3. Oh, because okay, in 5.3.3 it's supposed to modify GMRes.
Right.
Okay.
So guess I'm a little confused what we have to do differently.
Okay, actually very little. Because, well, for one thing, if you apply just GMRes without modification to a symmetric matrix, it will work. It will carry out MinRes. It's just that it's inefficient. Now, so the reason for that is when you have like GMRes is doing Gram-Schmidt orthogonalization. So but look at the main step in that. So what I'm doing right now, I have a GMRes algorithm in front of me. And a part of it that does Gram-Schmidt orthogonalization. We have so there's an outer loop that's over J. So now here's the inner loop for I that goes from 1 to J, and it's computing these entries of a Hessenberg matrix. So Qi transpose Bj, and then updating Bj. And it feels really weird saying Bj because in the chemistry department, there's a faculty member whose first name is BJ, who I just was just in a meeting with. So BJ equals BJ minus. Okay, Hij Qi. Okay. And the output of that is this Hessenberg matrix. that has this structure. Okay. And then zeros everywhere else. Now, but H, which is also Q transpose AQ, it just happens to equal that also. You're just not computing it that way. So that's GMRes. Now for MinRes, because H also satisfies that relationship for MinRes where A is symmetric, H is symmetric in that case. So for now a Hesterberg matrix that is also symmetric is going to be tridiagonal. So what that means is for a case of MinRes, you know before you even start that these entries up above are going to be 0. In other words, Hij for these ij will be 0. So don't compute them. So that's going to affect how this loop runs. So, so don't be going over ij where you know Hij is going to be 0. Don't be subtracting this off. So in fact, the actual change that you would make to GMRes to get a decent implementation of MinRes is very little. So
Can you repeat that again? You said don't be going over Hij knowing that what will be 0.
yeah, so since you know that Hij will be 0 for ij up here,
Yeah.
don't have this loop run through those combinations of ij. So tweak your loop, your index bounds.
This is the only thing to
Actually, yeah, that would do it. Yeah. So it's a short question.
I would not.
Okay. Right. Other homework questions?
5.3.2.
Okay. Oh, okay. Explain how the exact solution can be obtained if Hj plus 1j no longer applies. Okay. So, in that question, let's take a look at how Hj plus 1j is computed. It's a norm. It's a norm of some vector. So the loop keeps going as long as this quantity is strictly positive. So if it's not, what's the only other option? If it's a norm of vector, a norm cannot be negative. So so this point is always going to be greater than or equal to 0. So you have to look at so the thing is, what do you do in a case where Hj plus 1j equals 0? And I point you to a certain equation. So that's this one. So 5.16. Although the index I use there is k, but I'll just change it to j for this. So AQJ is equal to QJHJ plus HJ plus 1J QJ plus 1 EJ transpose. Okay. Now, so what happens in this case is you have this now being 0, and so if you have this situation now, how to solve AX equals B, and to answer that, what you need to take into account besides all this is that the first column of Q, so which can also be written this way, so QJE1, happens to be equal to B minus AX0 normalized. Okay. Now, and your solution, now your approximations, xk, have this form. Xk is equal to your initial guess plus, actually use j again for, okay. But these are only meant to produce approximate solutions. But now you can, in this situation, when you have this, you can try solving this exactly now. So what you can do is you can take your right-hand side expressing that using Q1, and that will help with that. And you're also using the fact that QJ has orthonormal columns. So QJ transpose QJ is identity. So see where that can take you. One thing you can try doing to convince yourself it's the exact solution, show that if you get a solution in this form, show that your residual in this case is actually 0. Because then you'd have the exact solution. Other questions? Okay. Make sure I'm not leaving anything out here, but I'm going to allow you to assume, since really it's a distraction from the main part of the problem, that the initial guess is 0. So it's less clutter. So forget about that. only one on the right side. Okay. All right, so now I can resume talking about computing eigenvalues in the QR algorithm. One thing I want to mention. On my webpage, I have a link on the left, textbook. And if you go to that, it's a webpage advertising a book. But the reason I'm pointing out to you guys is down at the bottom. There's a list of mistakes as I become aware of them. Sadly, it's a growing list. So this was an issue with the Chapter 4 homework. That I had messed something up in class, so I made you guys aware of it, what it's supposed to be, but then you went back to the book and used the wrong thing. So keep up with that, because, I mean, right now, most of the mistakes I'm finding are ones on the chapters I'm covering for you guys. So, and I really hope that mistakes are not that frequent for the rest of the book, otherwise it's going to be really embarrassing. But, really, most of the other chapters have been used in some class before, so. All right, so just want to make you aware of that. Okay, now. Okay. Now, where I left off last time was first version of the QR algorithm is so you choose an orthogonal Q naught. Any orthogonal, so which would be a square matrix. And I set T naught to be Q naught transpose A Q naught. So that is a similarity transformation. Now, you could choose Q naught to be any orthogonal matrix. For instance, you could choose it to be identity, in which case T naught would just be A. And it's repeated till convergence. And you compute the QR factorization of your matrix TK minus 1, and then come up with the next T by multiplying the factors in reverse order. So what will happen is, in most cases, not all, but generally speaking, TK will converge to real Schur form, and assuming that A is a real matrix to begin with. So I'll make that clear. A is the n by n real matrix, which might have complex eigenvalues. So it is block upper triangular, and all the blocks along the diagonal are 1 by 1 or 2 by 2. So 1 by 1 for real lambdas, real eigenvalues. For 2 by 2 for a complex conjugate pair of eigenvalues. Okay. So this is a start. That it's a way to obtain all the eigenvalues of A. But there are two significant problems with this method that make it impractical. First one, each iteration takes order n cubed point-to-point operations. To find n eigenvalues, you can expect to do on the order of roughly order n iterations. So the total amount of work, we're looking at order n to the fourth, which is just nuts. So it's much too slow. So I'm going to show you today how we can knock off an order of magnitude, knock it down to order n squared for the unsymmetric case. It'll actually be order n for the symmetric case. The second problem, which I hope to tackle on Wednesday, is that besides the fact that each iteration is too slow, too many iterations are being performed. The convergence of A to these TKs to this quasi-hypertriangular form is taking too long. So we need to find a way to accelerate the convergence, and that's what I'll show on Wednesday. Okay. So, so what can be done about the first thing, that each iteration is too expensive? Because a QR factorization for a general matrix, no getting around it, takes order n cubed operations. So the only way we can achieve a reduction, it has to be something that's a reduction in any case, is if we could carry out these QR factorizations on a matrix that has a simpler structure that makes QR cheaper in that case. So we have to do something up front. So to make each iteration practical, we do the following. Reduce A to Hessenberg form. So we want to reduce A to triangular form using similarity transformations. Now that is not something you can do in just one shot. It's not like Gaussian elimination, where you can just carry out some finite sequence of row operations and get it done. When you have to multiply on the left by a certain matrix and on the right by the inverse, you're a lot more limited in what you can do in a finite number of steps. So, but this is something we can do in a finite number of steps. Reduce it to almost upper triangular. There's this one extra diagonal that we still have to contend with. And then, once we've done that, we're performing QR factorization on a Hessenberg matrix instead of a general matrix. That takes only order n squared operations. So So now the number of iterations is still going to be out of hand, because that's something I'll deal with on Wednesday. But at least each iteration of those too many will take less work. So right off the bat, that's going to reduce the work by a factor of about n, which is great if n is large. So all I'm really saying here is it's still the same kind of QR factorization. It's just that when it's a Hessenberg matrix, we can take that into account and implement QR in such a way that we actually realize those savings. So the fact that there's only a few subdiagonal entries to eliminate allows us to carry out QR much more easily. Also, let's suppose I do whatever I need to do here to make T naught a Hessenberg matrix. So then I get my cheaper QR factorization down here. But then I compute T1. How do I know that T1 is also going to be Hessenberg, so that the savings will continue into the next iteration? Now, it turns out it does work out that way, that if you take a Hessenberg matrix, QR factorize it, and then multiply factors in reverse order, the result will be another Hessenberg matrix, but I have to show that. Okay. So first we'll deal with like how do we reduce A to a Hessenberg matrix? So what happens is, I can show you how to the structure of A as we work on it to try to zero out the entries that need zeroing. So I'll have a 6 by 6 general matrix. So at the beginning, we don't have any non-zero entries. Oh, I need one more column. Get real tired hearing that noise, I know. Okay. What I really need is a stamp. Okay. All right. What? Yeah. Okay. All right. So what I want to do is I want to make this portion 0. So, and I need to make sure that whatever I multiply A by on the left, I have to multiply by the inverse on the right, because it has to be a similarity transformation. And naturally, we would want orthogonal similarity transformations. Now, let's dissect this requirement. Orthogonal similarity transformations. They have to be similarity transformations because what do similarity transformations do, everybody? I remember stuck in your head. Preserves eigenvalues. So thank you for remembering that from 1 week to the next. That's a lot better than the 10 minutes that you guys did last time. Okay. So they preserve eigenvalues. Why orthogonal? If I have to multiply by a certain matrix on one side, then I must multiply by its inverse on the other side. Why do I want orthogonal? Why is that helpful? What do we know about orthogonal matrices and inverses? They're not the same. Although it's householder, but it is its own inverse. But in general, what's the inverse of an orthogonal matrix? What was it?
The transpose.
Yes, because you have Q transpose Q is identity. Therefore, if I multiply both sides by, actually, really what this equation says is that if I multiply both sides by Q inverse, then I get Q transpose equals Q inverse. So, yeah, because normally getting the inverse is really hard, but if it's orthogonal, it's easy. You just take a transpose. Okay. So what I want to do is I want to multiply A by some sort of matrix on the left, or its transpose. So do something like this. And now I want to do another similarity transformation to that. And I keep going as much as I need to get some matrix H that is Hessenberg. So I get in total U transpose AU equal to H, where U is the product of all the transformations in order, written from left to right. So this is U, and that is U transpose. So that's the idea. I want some finite sequence of transformations that will zero out these entries. Now, what is an orthogonal matrix that we've seen that is good for zeroing out lots of entries? So what's a really destructive orthogonal matrix? I mean, there's only certain types of orthogonal matrices we've even seen, so what are they? For QR factorization. We could do QR factorization. What? There's householders one. What's the other one? Givens. All right. In terms of zeroing out entries, what does Givens do? If I do one Givens rotation, what does that accomplish? What? Piece? Yes. Okay. All right, because I wasn't sure what a matrix piece was. But yes, one entry of a matrix is what a Givens rotation zeroes out. What about householder? Yeah, it'll wipe out like almost all of a column. Yeah, so householders are one that are much more destructive. That's what we really want here because we got a whole bunch of these. So that's what we can do. We can go column by column. So, I'll let see what notation I used here. Oh, okay. I happen to use this notation. That never happens. So let P1 be a householder reflection that's designed to zero out A3-1, A4-1, etc. down to A-N-1. So the entire column except for the first two entries. So that's a contrast of QR. QR, we wanted to wipe out all the column except the first entry. So from the second one on down. But now we're starting one lower. And I'll explain why we do that in just a little bit. So if I do P1 transpose A, now I don't need to transpose because householder reflections are symmetric, but just to reinforce that it's the inverse. So it has this structure now, 0, 0, 0, 0, and then everything else. And then, yes, I know this is annoying. Okay. So that one householder reflection applied on the left does all this damage. So that's all well and good. But we have to be careful now. Because now we have to multiply this by a householder reflection on the right. And we have to make sure that multiplying by P1 on the right does not undo what we just accomplished here. Now, and how do we know it's going to happen? Because since, because the way householder reflection works is you take a vector, you want to wipe out everything with the first entry, and use that to get your V, because so P1 is identity minus 2 V1 V1 transpose, where V1 is a unit vector. And so if you're trying to make V1 in such a way that you only affect this part of a column, you're not touching this one at all, then the first row is untouched. So that means that the first component of V1 is going to be 0. It's the rest of the components that will get the job done here. So as a result, P1 is going to have this structure. It'll have a 1 up here, zeros down here, and up here. And then P1 tilde down here, which is also a householder reflection using the rest of V1. So it's an n minus 1 by n minus 1 matrix. So why is this important? This is important because multiplying by P1 on the left is not going to touch the first row. Multiplying by P1 on the right is not going to touch the first column. So this multiplication by P1 here will leave this first column alone. So it'll still have the zeros that I created by multiplying on the left. Now everything else is going to be messed with, but we had created these zeros there anyway. So the structure is exactly the same. I wish I could just take this and somehow copy and paste it. Because at some point my wrist is going to get tired.
You just pre-make them on like construction paper.
Oh
and
yeah,
just,
this yeah.
Sticky.
Yeah, this is what I get for improvising too much. But yeah.
But you have to do this often.
Yeah, every couple of years at least. Yeah. I'll keep that in
Start
mind.
with this. I'll make them for you.
Oh, okay, cool. So now the work in the first column is done. So now I can do multiply on the left. Yeah, good point. To work on the second column. So now, this is not touching the first 2 rows. Only rows 3 on down to wipe out everything below the third entry. So you can see how this is going to unfold. That I'm going to keep multiplying by householders on the left, the same householders on the right. And because I'm not going for upper triangular, I'm only going for Hessenberg, these household reflections applied left and right, they do not step on each other's toes. Whereas if I was greedy and I tried to make it go for upper triangularity, like if I tried to wipe out, make this 0 also, that would affect the first row. Therefore, when I multiply my P1 on the right, I would affect the first column and undo everything I just did. So being less ambitious about what you zero is what allows you to zero properly. So now I can describe the algorithm for the Hessenberg reduction. So first, I let U be my identity matrix, and my Hesterberg matrix will initially be A. Okay. And then I'm going to loop over the columns up to n minus 2. Reason why it's n minus 2, look at this matrix. I want to zero out all this. Last 2 columns, I don't care what's in them. I don't have to touch them at all. So that's why I stop at n minus 2. Whereas with Gaussian elimination, you stopped at n minus 1. Because you're going for upper triangular. So I need a householder vector that covers the entries of H, starting from, so for instance, when j is equal to 1, I want to go from 2 to the end. When j is equal to 2, I want to go from 3 to the end. So I start at j plus 1 all the way to the end, column j. So the same house function you used in the homework, although a lot of you had the slightly incorrect house function that would work in most cases, but so you'll be hearing about that later. And then if I make this constant, C equals 2 over V transpose V, because I have this 2 from the household reflection, and V is not necessarily a unit vector, so this effectively makes it a unit vector. So then I can do H is a household reflection described by V applied on the left. But I'm only affecting rows j plus 1 to the end. So, like when j equals 1, first row, not touching. And then columns, j to the end. Reason why is, would I go to apply the second household reflection? I don't want to bother with this part because it's already 0. Like, I want to work on this part of a column, but if I multiply, if I apply my household reflection to this column also, all I'm doing is linearly combining zeros. It's wasted effort. So I start from column J to the end. So, so I'm only concerned about rows that are being affected and columns that actually have non-zero stuff in them. So I'll have identity minus 2 or minus C VV transpose times this same matrix. All right, so I'm applying a household reflection on the left. Now, really, what I should do is distribute this through here, but I wanted to make clear the whole point is I'm applying a household reflection on the left. Then I apply it on the right also. So for that, again, which rows and columns are being affected? It's going to be all rows, and these columns, j plus 1 to the end. Times identity minus C VV transpose. Now, in this case, actually, we'll talk about something from a homework. I'm going to actually carry out a distribution in this case. The transpose. Okay. Now, I want to point out something that y'all did wrong in the homework. Well, or at least did inefficiently. Because in Householder QR, you coded up something just like this to update Q. You're applying householder reflections on the right. And I'll bet that when you put this expression in there, you probably got a warning, didn't you?
Yeah.
Yes. It told you to group these.
Something about Hermetian?
Yes.
Yeah.
Yes.
All right.
That was a whole 45-minute discussion.
Well, they deceived you. Well, on the one hand, they were right.
We just need to throw MATLAB out.
They were focusing on the wrong thing because, yeah, to guarantee that this matrix is Hermitian in terms of, in spite of round-off error, you should group those together. But here's why it's a bad idea to do that in this case. Because here we have a matrix, VV transpose. If you go ahead and group it like this, it'll form this matrix. Then it's going to do a matrix multiplication, which is how expensive? Order n. Yes, order n cubed. When we're trying to do the whole algorithm in order n cubed, but there's n iterations. So you just made the algorithm order n to the fourth by grouping it this way.
So we didn't need the parentheses at all.
No, actually you do need parentheses, but not there.
Oh.
Put the parentheses there. This is a map vex. Order n squared. Then multiplied by a vector, that's a outer product, order n squared. So grouping like that makes it more efficient. I didn't take off because it was still correct, but yeah. So beware of that MATLAB warning. Yeah. So. Okay. Yeah, so it's one of those good to know things. Okay. The other thing I want to point out is that this vector v keeps getting shorter from one iteration to the next. First time around, when j equals 1, it's n minus 1 length. Then n minus 2, n minus 3, and so forth. That's why it's also necessary to select the appropriate rows and columns of H, so you're not getting some mismatch of sizes. This matrix keeps getting smaller and smaller, so I'm multiplying it by fewer and fewer rows. And because it's getting smaller, when I apply it on the right, it's applied to fewer and fewer columns. Now, notice the difference here. J to n in this case, 1 to n in this case. That's because of the lack of symmetry in H. Here, I'm keeping only columns j through n because the columns to the left of it are 0. So it's an efficiency thing. Here, the rows, in these columns, all the rows can potentially have non-zero entries, so I have to include all of them. So the asymmetry of H leads to an asymmetry in the indexing. Okay, and that's the end of the algorithm. Well, actually, no. There's one more thing I could do. This updates H. What if I want to accumulate all the transformations to construct U? So for that, I I would use the same indexing to apply the household reflection only on the right for U, and then end it. That's the algorithm. So this carries out the Hessenberg reduction. Now, if you only care about the eigenvalues, you don't care about the full Schur decomposition, you don't care about the Schur vectors or the eigenvectors, you would not do this. So if you're just trying to reduce A to quasi-rectangular form and recover only its eigenvalues, you don't need to accumulate transformations. And because that part is significantly more expensive, so it's important to think about, do you want to do that? So any questions about the Hessenberg reduction? All right, so it's just big old householder fest. And you get this Hessenberg matrix. So once you have that, you want to compute its QR factorization. And then you want to multiply the factors in reverse order. So let's suppose we have this Hessenberg matrix now, where I've zeroed out these entries below the subdiagonal. Okay. So, well, my zeros are a little misaligned. Okay. Now, I want to reduce this to upper triangular form. But there's very few entries I need to wipe out. It's only these. That one subdiagonal. n-1 entries that I have to wipe out. So what kind of matrix should I use to wipe those out? Yes, because Givens wipes out one piece at a time. Yep. Yes, you're never living at that. So I can use n-1 Givens row rotations to zero out each of those entries. Okay, so I'll start writing the algorithm here. So I'm working on columns 1 to n-1. So I find my Givens pair, my cosine sine pair, with entries h, j, j, the diagonal entry, and then the entry right below it. Those are the entries that I want to zero out. So then I'm going to perform a Givens rotation on rows j and j plus 1. So if I form this Givens rotation using a cosine sine pair, then all I have to do is update only rows j and j plus 1, and only columns j to the end, because otherwise to the left of that, it's going to be zeros. So I multiply the left by gj transpose. So I'm rotating rows j and j plus 1. Whoops. Just to wipe out that entry. And so this is enough to compute the QR factorization. Or at least it gives me the R part. It reduces H to upper triangular form. But I'm not done, because remember, anything I multiply by on the left, I have to multiply by the transpose on the right. because this is a similarity transformation I have to do here. So apologizing once again for my terrible board use. The algorithm continues up here. So this part is just the H equals QR. Now I have to do H equals RQ. Okay. Now, so that's going to be another loop. So first I'll set Q equal to identity as a starting point. And then I'll have another loop. So, and what that entails is multiplying the appropriate rows and columns. So rows 1 to j plus 1, and columns j to j plus 1. So just as multiplying on the left worked on only 2 rows, multiplying on the right will affect only 2 columns. So multiplying by the same gj on the right. And then, if I want to accumulate transformations, I do the same thing on Q. That's it. So, if I let, hold on, I'll wait till people are done writing.
Doctor, this is not necessarily a square matrix, right?
Not necessarily what?
A square matrix is not, right?
Oh, yeah, it is.
It is always.
Yeah, only square matrices have eigenvalues. Yeah. Because your lambda j will have the same number of entries as the columns. Or like, if it like ax equals lambda x. Ax has number of entries equal to the rows. X has number of entries equal to the columns. They have to be equal. Okay. Now, Gj is only a 2 by 2 matrix. So if I let Gj tilde equal to identity of size j minus 1, then Gj, 2 by 2 embedded here, and then another identity, which is n minus 2. Make sure I have this right. Like when j is equal to 1, oh, so n minus 1 minus j. Okay. So all the dimensions will add up to n. And zeros everywhere else. Then what's really happening here is I have G1 transpose, the G tilde 1 transpose up to G n minus 1 transpose H is equal to R. And all of this is Q transpose. Now, the only reason I'm introducing a tildes is to make each matrix, each of these matrices have to be n by n. So I can describe everything in terms of n by n matrices. So this is what the first loop is doing. It's multiplying by these to reduce H to upper triangular form. Then my new H is my R times G1 tilde, G2 tilde, up to Gn minus 1 tilde. That's Q. To handle the multiplication on the right by Q to multiply with factors in reverse order. Now, what's very important here is that the only reason this is done efficiently is because Q is I never actually multiply by Q in full. I multiply by Q in stages, these individual Gibbons rotations. Because if I formed Q in its entirety and then multiplied R times Q, that's an order n cubed operation. That's matrix-matrix multiplication. But leaving it this way as a product of Gibbons rotations, each of which is really cheap, each Gibbons rotation is order n operations. This whole process makes order n squared work instead of order n cubed. So knowing how a matrix breaks down into individual operations is very helpful for improving efficiency. Now, I mean, if I want the eigenvectors later, then I do want Q for later. But at first, just getting the eigenvalues, representing Q implicitly in terms of all these Gibbons rotations, that's good enough, and that's actually more efficient. Actually, in terms of computation time and storage, because I can store the C's and S's, and from that I could reconstruct Q if I wanted, but that's a lot less numbers to store. It's only storing 2n minus 2 numbers instead of n squared numbers for the whole matrix. Now, one other thing that's worth pointing out about this algorithm, notice I do all the row rotations first to make H upper triangular. Then I apply all the column rotations in a separate loop after that. You might think, why does that have to be done that way? Why not do a row rotation, then a column rotation, then another row, another column, just keep alternating like that? Because that way I wouldn't have to store these in this loop to use in this loop. But it turns out that's not going to be correct because these rotations step on each other's toes. If I do a row rotation, then do the corresponding column rotation, the matrix is now changed, which affects the second row rotation. It throws it off. So the sequence has to be like this. All the row rotations, then all the column rotations to get the correct result. So it's very important to pay attention to when you perform like a Gibbons rotation or a household reflection, what part of the matrix is it affecting? And is it going to throw off something else you want to do? And that's something I'm going to show you now to explain why, if I start with a Hessenberg matrix and I do all this, why do I still have a Hessenberg matrix at the end? So, let's suppose I've done this first part. I've computed QR factorization of H. And Q is a product of Gibbons rotations. Now, why is my new H, which is equal to RQ, also Hessenberg? How do we know that? The key is each one of these Gibbons rotations, row rotation if it's multiplied on the left, column rotation if it's multiplied on the right, only affects rows or columns J and J plus 1. It's going to rotate those rows or those columns. That's going to be essential here. So if I consider H times G1 tilde, and I write out what H, well, actually not H, I want R. Because I'm multiplying R by all these given rotations. So R is upper triangular. Now, so when I apply G1 tilde on the right, it's only going to affect columns 1 and 2. So it's going to make each one of these columns a linear combination of these two. So the upper columns will not be affected, so I'll just fill those in now. So if I make each one of these two columns linear combination of the first two columns, which entries could possibly be non-zero? What are the only ones that could possibly be?
Row 2, column 1.
Yeah?
Not that one.
What?
That was still be 0.
Well, you're taking these columns.
Linear combination of, okay, that would be X.
Yeah. Well, what else?
That's the top, the very top one. That's all. The others will be 0. And then,
also.
yeah.
Yeah. Anything else?
No.
Yeah, because you're combining zeros. So the first column can only have these two non-zero entries, which is Hessenberg. Then you move to the next rotation, G2 tilde, which affects these two columns. First column will never be touched again. Here, yes, never. So this might slide over here, but it's still consistent with Hessenberg form. So that's the idea, that I keep applying given rotations because of what they touch and don't touch. That's why the result is going to be Hessenberg. So that Hessenberg form is preserved from one iteration to the next. But the ultimate goal of eventually some of these subdiagonal entries really becoming 0 to get to not just Hessenberg, but triangular. But that's something that will take a while. So that's why this Hessenberg QR operation of H equals QR, then H equals RQ, will only take order n squared operations. So now each iteration of a QR algorithm is cheaper. It's there's still too many iterations, but again, that's a topic for Wednesday. So any questions about that? Oh, do you have a question? Now, if I go back to this general Hessenberg matrix, what if one of these subdiagonal entries actually becomes 0? Let's suppose that this is 0, or so small we can declare it to be 0. That's actually a huge development, because then the matrix breaks down like that. So as soon as a subdiagonal entry becomes 0, we have what's called decoupling. The eigenvalue problem is now blocked upper triangular. So the eigenvalue problem is decomposed into two smaller problems. I can focus on getting eigenvalues in that 3 by 3. and this is 3 by 3. So anytime a 0 appears on the subdiagonal as a result of doing this QR of an RQ, that's a very welcome development because it means your problem's got smaller. You're actually zeroing in, literally, on those eigenvalues. So that means you only want to do this QR step on a matrix, or a portion of this matrix, where all the subdiagonal entries are still 0. You don't want to keep doing it on the whole thing. That's wasteful. So for the rest of today, I'm going to talk about a specific type of Hessenberg matrix. Where all the subdiagonal entries are non-zero. So Hessenberg matrix H is said to be unreduced if all of the subdiagonal entries are non-zero. So, okay. So we only want. So the idea is, as we keep doing this QR algorithm step, we're going to watch for zeros to appear on the subdiagonal. Then, what we'll do is, as zeros appear, we're going to pick out some block of H along the diagonal that's still unreduced and keep working on it to try to reveal more of the eigenvalues. So unreduced Hessenberg matrices are of particular interest, but there's one property of unreduced Hessenberg matrices that can be very useful to us on Wednesday. The implicit Q theorem, which is the only thing I've ever seen in numerical linear algebra that sounds somewhat James Bond-like. But it's actually a really cool theorem. I'm hoping I can give you an idea of a proof by the time we're done today. So let's suppose we have some n by n matrix A and orthogonal matrices V and Q. And they both reduce A to Hessenberg form. And I'm going to assume that H, this Hesterberg form, is unreduced. And I'm going to break down the columns of Q and V. So Q has Q1, Q2, Qn, V1, V2, Vn. And I'm also going to assume, lots of assumptions here, Q1 is equal to V1. So these transformations that reduce A to Hesterberg form, let's suppose the first columns of those match. Then it turns out if the first ones are equal, then all of them are equal, at least except possibly for sign change. In other words, they're at least parallel. So we're pointing in the same direction or opposite directions. The Hessenberg forms are equal, except possibly for sign, which means that G also is unreduced. So in other words, we say, in this case, we say that these are essentially equal. So this implicit Q theorem is really describing like a uniqueness of the Hessenberg reduction. That the transformation that reduces A to Hessenberg form is pretty much entirely determined by the first column. And that's something that's going to be, it's really the only reason we have an effective algorithm for computing eigenvalues of a general matrix, even if they're complex. Without this, it just wouldn't happen. So it really was something that saved the day, as I'll get into on Wednesday. But what I want to take whatever time I have left to do here, I think I can pull it off, is to show where the rest of my pages went. Oh, okay. Is to give you an idea, at least an outline of a proof of this theorem. Okay, so I have AQ equals QH, or actually, wait, I don't want to do that. So I don't have the steps written in front of me, so I'm doing this from memory. So it's going to suck, but, okay. So G, which is B transpose AV, but I could substitute for A. A, from the other decomposition, is QH, Q transpose. Just by rearranging this. So, so now I'm going to use the fact that Q and V are both orthogonal. Do the following. I'm going to multiply on the right by V transpose. And then I'm going to multiply on the right by Q. So then I have V transpose Q H. Because when I multiply on the right by V transpose, it cancels the V. And then if I multiply on the right by Q, it cancels the Q transpose. Because they're orthogonal. So I'm going to call this W. So GW is equal to WH. So that's how the two are related. Furthermore, W is orthogonal. And the reason why is, whoops, sorry to whoever watches this later. So the reason why W is orthogonal is anytime you take orthogonal matrices, you multiply, the product of orthogonal matrices is also orthogonal, which actually I've used many times because we have this product of sequences of orthogonal matrices. Okay, now the next thing I want to do is I want to take a look at, I get some understanding about W. So I'm going to look at the first column of both sides of this equation. So GWE1 is WH E1. Now, one thing I can tell you about W is, okay. If I look at WE1, that's the same as V transpose QE1. But the first column of Q is Q1. Now, V has the same first column as Q. All the other columns of V must be orthogonal to it. So, column is E1. Now, to give you an idea, all right, so that's the same as V1 transpose, V2 transpose, down to Vn transpose times Q1. V1 is Q1. Q1 transpose Q1 is 1. It's a unit vector. All these vectors, V2 to Vn, are orthogonal to V1. But V1 is Q1, so they're orthogonal to Q1 also. That's why I get 1, 0s. Okay. So the first column of W is E1. So now I get GE1 is WH E1. Now, G is a Hessenberg matrix. Oh boy. So, GE1, G is a Hessenberg matrix, so it only has G11, G21, rest zeros. And WHE1 is equal to W times first column of H, which is H11, H21, zeros. And I know that that's non-zero. Now, what is this matrix vector product doing? Is it's taking the first column of W times H11 plus the second column of W times H21. Is equal to all this. Okay. Now, I know what W1 is. That's E1. I don't know about W2, but I can solve for it now. So W2 is equal to this column here minus this, so minus H11, and then I have nothing else to subtract off, all divided by H21. And I know I can do that because H is unreduced, and therefore H21 is non-zero. So that assumption is essential. Now, notice only the first two entries can be non-zero. So, continuing this process. Okay, yep, I'll finish in time. We find that W is upper triangular. Because notice the first column had only one non-zero entry. The second column had only two non-zero entries. If I continued, it would keep going like that. But a matrix as orthogonal and upper triangular has to be a diagonal matrix. Reason why is, for an orthogonal matrix, the inverse equals the transpose. The inverse of an upper triangular matrix is upper triangular. The transpose is lower triangular. The only way an upper and lower triangular matrix can be equal is if both are diagonal. But besides that, because it's orthogonal, the diagonal W, all the entries are plus or minus 1. So it's not just any diagonal matrix, it has to fit that form. Just for sake of orthogonality, it's a real orthogonal matrix. So you have the squares of the diagonal entries must be equal to 1, because Q transpose Q is identity. So Qj transpose Vj has to equal plus or minus 1. But so the fact that it's a diagonal matrix in the first place, that shows that these guys are parallel, and the inner product can be plus or minus 1. That just means that they're scalar multiples of each other, so either equal or they're negatives of each other. So this is what tells you that Qj is equal to plus or minus Vj. And finally, Hij is equal to Qi transpose AQj, and Gij is equal to Vi transpose AVj. So if the Q's and V's are plus or minus each other, that tells you that Hij is equal to plus or minus Gij. So that's what leads to these Hessenberg reductions being essentially equal. So they agree up to this sign. So that's the implicit Q theorem. Right now it's just like, oh, that's a rather freaky result, but it's something that'll become essential to us on Wednesday. So, and I ran 1 minute past. Sorry. When I know that all of my colleagues will gladly go on for 10 minutes and not blink or apologize, but whatever on that. So, okay, so until then.